So I was asked to talk about observation estimates, essentially the size scale of structures in the CGM. And so we're going to talk about, I think we're going to start first with what are we actually measuring here, and then go through a number of approaches that are available to make some estimates of the size scales of structures in the CGM. Now, a couple things. Firstly, I'm also going to talk, and I'll spend quite a bit actually on the galactic interstellar medium, because there have been a lot more measurements in some regards in the galactic interstellar medium, and plus the precision, the sort of measurement scale is smaller. But also, this was, is not my area in some ways. It's something I've worked on before, but please do not be offended if you don't see a seminal result up there, and let us know. We can talk about it in the breakout room. So I guess one thing that struck me when I was thinking about this was, I mean, we have to discuss at some level what we're measuring. And typically the way that many of these measurements are made is that we're assessing some length scale over which the column densities or perhaps the kinematics vary in some significant way. And that significance, what we mean by that, varies from measurement to measurement. The other thing is, even when we're doing direct imaging of clouds, we're often measuring some sort of size of a cloud, and that definition can be nebulous. There's some, when you have an H1 data cube, you're able to define that a little better perhaps, but there are definitely definitional aspects of that. And it often will depend on angular resolution and column density sensitivity. And Mary Putman talked about this with regards to the complex C and Magellan extreme results a couple of weeks ago. So if we start at the Milky Way, there are sort of some primary ways in which we get information about small scale structure in the interstellar medium of the Milky Way. And they rely on thinking about the spatial sensitivity of, or spatial variations in column densities, or at least from the absorption line-based methods, that rely on either one of two methods. One is thinking about temporal variations, where you have a background source that's moving with respect to a foreground cloud. The cloud can have some motion as well. And this can even take the form of a binary star, because the binary, as it goes around its orbit, you're probing different sight lines through the foreground Milky Way. And so that puts an upper limit on the size scale of the structures you're probing of essentially twice the orbital semi-major axis of the binary. And some of this has even been done, for example, in the radio using pulsars as they zip across the sky. And we can see absorption of 21 centimeter against the pulsars to give us some estimate of the changes in that column, or in that absorbed optical depth as a function of time. The other is to rely on spatial variation. So you're measuring multiple sight lines through some foreground cloud. And this was kind of first done in the 50s, actually, but there's a long history of doing this, both in the Milky Way and thinking about multiple sight lines to quasars in the CGM of more distant galaxies. Now, I should point out that there is a really nice review of sort of microstructures in the diffuse interstellar medium of the Milky Way by Snez and Ellen that appeared in 2018. Now, they're talking about size scales of not only sub-parsec, but sub-AU in some cases that we get sensitivity to. The TSAS is tiny scale atomic structure here. CNM stuff is sort of the sodium-1 and other things that you would pick up in absorption. And then extreme scattering events come from usually studies of pulsars and such. So between scintillation and measurements of, for example, the optical depth of H1 against radial lobes and how that changes in time and in space. Even the temporal type variations that you can see sometimes. Here's, for example, some of the work by Dave Meyer showing the absorption from this specific cloud that we know to be a foreground, very small scale thing in the local bubble, but that varies in time. So these microstructures that get discussed in here are typically thought of as either tracing the turbulent cascade of energy down to very, very small scales, or even thermal instabilities. And they're often found to be overpressurized with respect to their surroundings. So they're perhaps transient in some ways. I'm not going to discuss a lot of that because that gets way down on the size scale. But there's another reason for not spending a lot of time on this. So this is just to focus on some of the stuff that the Northwestern group led by Dave Meyer did over the last few years. And one of the things they did was take an IFU, the dense pack at WIN, which is, tens of arc seconds on a side essentially, and just point it at a globular cluster and look at the variation in the column density of sodium-1 as they look across that cluster. And what they find is factors of 2 type variations in those column densities over sort of a few thousand AU type size scales. It's not ubiquitous, and the sort of total amount is, it depends on which direction you're looking, but in a couple globular clusters, they've seen this with some regularity. But part of the reason I'm not going to spend a lot of time on those sort of very, very small structures is that the thinking, at least in the Milky Way crowd right now, or at least our understanding of it, based on things like binary stars that are separated by a few thousand AU, is that while we see these variations in the cold neutral gas, the very, very densest, coolest gas, and in the non-dominant ionization stages of gas, such as sodium-1, carbon-1, magnesium-1, things like this, the changes don't seem to be present to a large degree in the dominant ionization stages that we see, things like that we're used to seeing in the low ions, things like zinc-2 and magnesium-2 and such. And so it seems that the structures in the warm neutral medium are significantly larger than this few thousand AU. Now, again, part of this depends on what your definition is and how we're measuring this. It's important to remember that all we're doing at some level is seeking and looking for, and in some cases measuring, column density variations over some spatial scale. But it doesn't seem like those are predominant or particularly important in the warm neutral medium. Now, in the local group and a little beyond, we can actually do direct imaging of clouds that gives us some handle on the size scale. So this, for example, is a look at one of the at a tangent point velocity. So we know the distance to the gas, just a section of the thin disk and thick disk in the interstellar medium. We saw this plot a little earlier from Jay Lockman, also showing the Smith cloud. And typically what we find in the Milky Way is that these H1 clouds, or they're likely cloud complexes with some substructure that's just not quite resolved here, or we're not measuring the fine scale structure, but typical sizes are of order a few tens of parsecs or so. This is, again, showing the work by Xu et al. From 2011 that Mary showed. And one thing I want to point out here is that, these are probably pretty reasonable sizes that get measured, again, a few tens of parsecs at complex C, because the resolution is very far down here. But we also do find that, as Mary emphasized too in the work by Bart Walker and some others, that as you go to interferometry data and you look, you will find structure on many, many scales as you go further down. So this is sort of a definitional, well, at some level, a definitional problem that says, when we make this measurement, what's the full width half max at some column density sensitivity, or what's the sort of total cloud extent at that level? I wanted to have a brief interlude here too for just to talk about the M31, M33 system, because this map by Braun and Dilker that came out in the early 2000s has been mentioned a few times over the last couple of weeks. And one has to be a little cautious with this, because so they imaged the M31, M33 system using Westerbork in a total power mode, and effectively use sort of very large spatial scales and very large velocity scales, it turns out, to integrate in order to get to very low column densities. And one of the things that happened in that case was they picked up both some residual emission from the Milky Way in the spatial direction, but especially in the velocity smoothing that they did, that brought in emission from the side lobes that looked like it had the right velocities to be associated with the M31, M33 system. So a lot of this material is not quite real anymore. And in fact, when you do see the stuff that is real, it is on much, much smaller scales than will be implied by the structures that you tend to pick out in this. So this is work by Sidney Wolf and others, and just showing that again, you can resolve some of this emission into extremely small clouds from the standpoint of the scale that was shown here. But even those likely have substructure that we're not quite measuring yet. I will say it is possible then to, in the sort of warm neutral medium and a little bit of the cold neutral medium in nearby galaxies, look directly at traces of that either in H alpha for the warm ionized medium, or in things like the dust structures that you see in the thick disk of edge-on spiral galaxies and such. And we typically find that, once again, typical structures, the smallest clouds, probably a resolution limited statement, have, a few tens of parsec type scales. And the complexes that house them have, sort of 100 to almost kiloparsec type scales. All right, if we move on to the transition temperature gas, so this is sort of gas traced by O6, carbon-4 perhaps and such, it appears that the transition temperature gas in the Milky Way varies on sort of 10 to 100 parsec scales. And that statement may be a function of the ion that you're actually using to probe this, just because they probe different energetics in the Milky Way. Certainly we know that the transition temperature gas traced by O6 at least has structure on degree type time scale, length scales, angular scales. along high latitude sightlines, but not on arc-minute type scales. So we, many years ago, used the fuse data in the large and small Magellanic Cloud to measure O6 coming from the Milky Way towards a few tens of stars. And when you do that and take pairwise comparisons of the oxygen-6 column densities, the difference that you get in that oxygen-6 column, this is the difference in the log here, as a function of angular size is plotted here. And you can see factors of 50% variation on all angular scales throughout this, essentially. The dispersion of the O6 column densities in the Milky Way is about 30 to 40%. So there's a lot of bouncing around, even in this relatively small angular part of the sky. Variations are seen in all velocities. That includes both the low velocity gas, the intermediate velocity gas, high velocity gas. So there is a lot of structure in this. When you do an autocorrelation, you find there's no sort of preferred scale for this down to the smallest scales that we can measure. Now, if you make the assumption that O6 resides within about 5 kiloparsecs of the disk, which is kind of what you expect for high velocity clouds and such, and it's a few times this typical scale height that's calculated for the oxygen-6 in the Milky Way, then the scales that you're talking about here are sort of less than a few tens of parsecs typically. Now, I will say we try to do this on an even smaller scale where we use these, I love this, we use post-extreme horizontal branch stars in this globular cluster. This is an ultraviolet image from the UIT instrument that flew on the shuttle. And at this distance, each of these stars, one arc minute is about a kiloparsec separation. So we were probing scales down to about 2 to 10 kiloparsecs or so. And we didn't see any evidence for any structure in the O6 with sort of variations on the 25% level or more on these sort of less than 10 parsec scales. Now, we don't know exactly where this gas is. It resides at velocities that probably place it in the disk and the low, thick disk of the Milky Way. Certainly no larger than the height of this globular cluster, which was about 2 kiloparsecs up or so. All right, and there's one other way to sort of estimate the scale of O6 in the Milky Way that I found really interesting. One of the things that happened was Fuse had 2 apertures, well, 3 apertures, but 2 that were used at all. And for really bright stars, you would use sort of a slit-like aperture, and that left your large 30 arcsecond aperture pointed in some random direction in the sky. And because of that, people, Van Dixon and Ravi Sankrit and others, put together all those data that were just making blank sky observations throughout the galaxy and look for oxygen-6, diffuse oxygen-6 in emission from the Milky Way. And there were a couple ways in which they estimated the size scales of the emitting regions. The first was, if you just do this sort of standard thing of saying, well, look, the mean density is something like the emission measure over the column density, and if you divide the column density by the mean density, so that's column density squared over EM, you get some measure of a length scale, as long as you're sort of assuming that the conditions don't vary by some huge amount there. And they did this all over the sky in their sort of 30 detected regions, but in particular in a couple of directions that saw emission from complex C and the Magellanic Stream, they can make some crude estimates of what was the sort of typical length scale of the emitting regions. And they come out to be of order, again, 10 to maybe 100 parsecs or so, depending on the assumptions that you make. It's a little crude because they didn't have absorption measurements along exactly the same sightlines, but, of course, you do what you can. Now, the other one that, and I have to say, I've talked to them about this measurement since, and while it comes off as very positive and robust in their paper, they're a little dodgy about it now when they think back on it. But one of the cool things that you can do is Fuse has an aperture size of about 30 kilometers per second. And when you convolve that, the essentially square line spread function you can get from a pure 30 arcsecond wide aperture with instrumental spread function, you should get a line that looks something like this. It's sort of a Gaussian convolve with the top hat, and it should be about 100 kilometers per second across. And what they found was that in about a third or so of the directions where they detected O6 in emission, the width of the emission lines that they detected was smaller than they would expect for a completely filled aperture. And so if you make some calculations to say, well, what fraction of the aperture would have to be filled in order to get the lines as narrow as we see them, they come up with some extremely small size scales. So if the typical size scale they measure is something like 20 arcseconds across instead of the full 30 arcseconds of the beam. And if you think that sort of gives you the full size scale of the less than, sort of a 20 arcsecond or so size for the O6 emitting regions that they're viewing, these can potentially correspond to some very small size scales. Now, this is at some level a density weighted measurement as opposed to density squared weighted measurement as opposed to a density weighted measurement like you might otherwise get. But nonetheless, it's kind of intriguing that there may be some extremely small filaments, even in these sort of transition temperature regions that, in order to be excited, have to be pretty much at 10 to the 5th Kelvin or above. All right, so if we move out then to think about what we learn about the CGM from quasar absorption line things, I mean, a lot of us were introduced to this idea by Michael Howk and the work that he did over the years. He started looking at, and other people had done this before, but I think this was sort of when at least it got into my brain. Maybe it was because of my age or something. But he started looking at lens quasars and looking at the structures in magnesium-2 systems in particular. And this just shows a series from this famous Einstein cross of sort of a redshift of roughly a half system. And what he argued was that, look, you can trace the complexes of magnesium-2 over distances that are sort of half a kiloparsec to a kiloparsec, something like that. So complexes are correlated on large scales. But the individual cloudlets, so looking at the individual components in here, for example, are difficult to trace over more than a few hundred parsecs. Now, this distinction about this, these are Keck high-res data. This distinction about how you look at absorption lines like this, and it can actually ask if they're changing both in velocity and in total column density or equivalent width, might get lost at low spectral resolution. So it's something to be aware of as we move forward with a lot of the work that we're doing with IFUs. I should say too, there have been some attempts to do this via temporal changes. There was an upper limit for the low ionization stuff, and Art back in the 80s published a potential sort of case of H121 centimeter variability on sort of AU type times length scales based on the timing. But they were never quite clear what the origin of that was. There's been a lot of work done more recently looking at sort of lensed quasars to probe foreground CGM in other galaxies. And a lot of the time, just depending on the separation of these quasars, but typically when we're able to do this, most of those are sort of probing 5 to 10 type kiloparsec time scale. So again, they're telling you about large scale correlations of the absorption, but they're not often giving quite as much information about the very smallest scales. If you go from the low ionization state absorbers to the higher ionization state gas, this shows another plot from another Howk paper in the late 90s. And what you can see is in the carbon-2 and silicon-2, for example, there are components that come and go in various ways, but the carbon-4 and silicon-4 tend to be much more in agreement between the two sight lines that were observed. And in fact, he has this nice plot of essentially the fractional change in the column density as a function of the transverse separation of sight lines. This is even just from one sight line, of course, for gravitationally lensed quasars, that you're seeing different separations depending on the redshift. But you'll see you don't get maybe to 50% type variation for the most part until you get above about a kiloparsec or so. And this comes up too with oxygen 6, and this is a paper from Sebastian Lopez that shows in black and in blue here 2 different sight lines for various redshifts. This is oxygen 6 in absorption, and they also are arguing that the quote-unquote coherence length of the oxygen 6 should be bigger than about a kiloparsec. Kate Rubin in a 2018 paper had a nice little summary of sort of the picture of this. On the left is the fractional difference in the equivalent width coming from magnesium-2 or iron-2, so low ionization state gas. And on the right, you see the same quantity for carbon-4. Now, I should say, as you get lower on this plot, that means a larger difference between 2 sight lines probed by gravitationally lensed quasars. And what you can see is in the low ionization state gas, at all physical scales, there's sort of a lot of, it's sort of filling this whole space. And when you go to carbon-4, though, as you look at the small physical separations, there's a lot less of this space occupied. Okay, and so that's just implying that the typical size scales over which carbon-4 varies are somewhat larger than you see in the low ionization state gas. So, last 2 things here. Let me talk a little bit about density estimates, or density-based estimates for size scales that come from photoionization modeling. So, these all are going to depend on the assumed radiation field intensity in particular. But if you understand that, you can make some path length estimate for the length of your sight line through a bit of low ionization gas. Now, it's a little, well, let's look at it this way. If you think about this as sort of a quote-unquote realistic cloud or structure, where it has some density variation within it, maybe a high density core and some lower density in the wing. So the density as a function of distance might look something like this. In the core, where the density is high, you're going to prefer low ionization state gas, and as the density goes down, you're going to prefer higher ionization state gas. Now, when we do the modeling for this, most often, not always, but most often, we're sort of taking that core of the low ions and we're saying, okay, we're going to model this as a constant density structure, and it's going to have some length that goes through it. And in order to sort of account for the way in which we're cutting this out, we're only going to take out the lowest ionization or some mixture of ionization states that we think occurs in this high density core of the structure. So our model structure is a very, very, very much simplified version of this. And then we're going to say, well, look, the length scale we can calculate by taking some ion and measuring its column density, dividing that by the model-based column or density, physical density of that ion. Now, typically, if you did something like this, that for H1, you'd say, well, we measure an H1 column density. Our model gives us the particle density, and then we have an ionization fraction we also have to include in there in order to turn that sort of total particle density into an H1 particle density. Now, because of the way in which, I mean, really when we do these models, we're trying to match an ionization parameter, which is the ratio of photon density to particle density. And so your density that you get down here for the model at some level depends on your normalization of the intensity in the photoionizing radiation field. But nonetheless, some of us have been brave enough to actually, present the results from that. So Jess has been sort of brave enough. She's shown this at a number of conferences, but it didn't get into the paper. So this is the length scale for sort of the photoionization modeling that comes from the cost halos analysis. Fari Zahidi plotted or showed this as the density as a function of column density for the cost LRG survey that he led up, or that he and Xiaowen led up. And you can see lines of constant length scale in here. They give a sort of typical length of about 100 parsecs or so for the models that they have. And then Nico and collaborators in the CCC survey have a PDF essentially of the length scales that are involved in their modeling of line limit systems and partial line limit systems. So the sort of takeaway from this is that the low ionization state gas has scales of order, and let's say of order, 0.1 to even 10 kiloparsecs if you sort of take the 60% confidence intervals here, for example. But you have to remember too that this really is dependent on what strength of the radiation field you assume. And then lastly, just a couple sort of a hodgepodge of some things that I found really cool that I was in some ways less aware of as I started to put this together. There's some evidence from the fact that if you look at the continuum, the incidence of magnesium-2 absorption systems against the continuum of quasars, which arises in sort of a very narrow range of the accretion disk, versus the incidence of magnesium-2 systems that you see if you look only on the broad emission lines from quasars, that the statistics of those counting are the same. And so that gives you an estimate or sort of a lower limit on the length scale of the magnesium-2 absorbers, which is bigger than about a few thousand kiloparsecs, or a few thousand AU rather. Kate Rubin has a really nice paper where she's looked at essentially the incidence of magnesium-2 systems against background galaxies and asked the question, how big do the background galaxies have to get on the sky before you start to get statistics that are different than you get for sort of quasars? And that tells you something about again, what they refer to and what we often talk about as a coherence length of these. It's not necessarily telling you the sizes of the individual clouds, although it may, but it's telling you the sizes of the structures or the correlations of the magnesium-2 systems on the sky. And they get a number of about 2 kiloparsecs and more. And then Jeff Cookie and John O'Mara did this thing where they essentially they found a damp Lyman alpha system against the background galaxy and looked at whether essentially what the covering factor of that damp Lyman alpha system was against the background galaxy. And that gives you an estimate of the area of that absorption, which is a few to 100 square kiloparsecs, which is quite a bit. But again, this is more of a complex level idea. And then last, we've seen a proliferation recently of lots of measurements against arcs and such via strong gravitational lensing in clusters, where you can measure the magnesium-2 as a function of impact parameter or even azimuth from galaxies. And this strikes me as extraordinary because if you look at this plot from the most recent Sebastian Lopez et al. Paper, the magnesium-2 fall off from this individual CGM sort of follows what you get from sort of ensemble surveys of magnesium-2 absorption around galaxies. It shouldn't work that well. It shouldn't be kind of a monotonic fall off. I mean, it should be more bizarre and random than that, and yet it is. There's a very recent paper by Chris Mortensen and collaborators also find the same thing. These are the green points here. The Lopez points are on the black there. So again, while that doesn't tell you so much about the very fine scale of these magnesium-2 systems, what it does tell you is there are correlations on very large scales that are important. All right, so I'll just summarize here. I don't know where I am on time, so I hope I didn't go over too much. But in the Milky Way, the CNM and the non-dominant ionization states certainly vary on extremely small scales. The warm neutral medium gas, though, tends to be, or at least have consistent columnices across sort of tens of parsec type scales. Even though within that, there are probably things we're missing at relatively smaller scales. When we look at the transition temperature gas, it seems like the scales that are important there are sort of 10 parsecs and above. And you kind of see a similar behavior as you go to some of these larger scales in the CGM or in CGM measurements. That as you go from the magnesium-2 systems, the higher ionization state systems, you go to moving over larger scales. Certainly, we know that we think we know there's not structure on well below a parsec in magnesium-2 systems. But the thing that sort of intrigues me is they're certainly coherent over very large scales, even if we're not. We don't see them vary on sort of the smallest scales that we're looking for. So I'm happy to answer questions, and thanks for listening.
Thank you, Chris. Yeah, that was a good, comprehensive overview, and really just covering every size scale measurement of the CGM and more, and the ISM. That was about 25 minutes, so we won't take questions except in the breakout room, but this is our time for a break. So at 9:05, 5 after the hour, we are going to start John Davis's Baron clearing tutorial. So take a break or go out, go to the breakout room with Chris. And that was a very intense first hour. So excellent job by everyone. Thank you. So we'll be back here in about a little bit more than 5 minutes.